I'm recording.
Points for lateness that time.
Yeah.
Okay.
Okay.
But didn't reduce any points.
Yeah.
So this is EE490. We have Zach and Ben here in the room. If you're wondering who I'm talking to,
Yeah.
Pre-lecture 8 was due today. You get a whole week of no pre-lectures that I had scheduled for spring break. My 280 students had to break the news to me yesterday. There is no spring break. But there's no assignment scheduled, so we'll probably just carry on and talk more about Flash. Or I'll do something. I could add some more emerging memory stuff or do something like that. Pre-lecture 9 is due on Thursday. Homework 2 is due on Thursday. Your project 1 has been graded, and I emailed you why I took points off. There's only like a couple of people in the class who got a perfect score. If I took points off, it's because there's something I want you to fix before you start project 2, and it will help you. If your project name was wrong, you don't necessarily have to fix that as long as I could find it. There have been people who their project name was wrong, but they had like 5, 10 projects in there, and I couldn't find their project because I didn't know which one it was. I've taken points off for that, for having to dig. Homework 3 is due 2 weeks out from that one, and then project 2 is due. Project 2 is significantly more difficult than project 1. You have to take your project 1, add some stuff to it. You're going to create a test bench. There's going to be a lot of pulse sources in there, a lot of DC sources. There is something to turn in on BB Learn. You have to hand sketch or otherwise draw a timing diagram of what you think your pulse sources should look like, and use that to set up your pulse sources. Otherwise, it'll drive you crazy. I know I've done this. I've actually done the whole project myself. And then the midterm exam is coming Tuesday, March 9th. Normally the week after that would be spring break, so we'll have a pseudo spring break in here. We'll have classes, but nothing's going to be due. You can kind of catch up on your other stuff. Ben wants to watch Bill and Ted. Okay. A real movie we're going to watch on Monday, February 15th at 5:30 p.m. You can either come into the cave, EGR 237, or log into my Zoom. This was when COVID first started, somewhere in like April or May, when we started going stir crazy, we started watching movies through Zoom, and it does work. So Ben's going to stream it. It'll go through my Zoom. We're going to watch Asterix the Gaul. Asterix, well, it's Asterix the Gaul and Asterix in the Magic Potion. They actually made Legos out of this. This is what I love. It's not a Lego movie. This will be a good movie. Lego movie.
Fantastic.
He's a cartoon character, obviously French. We found an English translation of this. I easily found when me and Ben first came up with this. Of course, this is what happens when you let us go open loop. I easily found a French version of this, a Czechoslovakian version of this, and an Arabic version of this movie. Oh, there's a Hungarian version too. So it's popular all around the world. And it's a cartoon movie. If it's boring, we'll just sit there and talk. Okay.
Yeah.
But it's funny.
It's funny. It's
cartoons comic books from when I was a kid.
Or newspapers sometimes.
I never saw them in the newspaper.
I occasionally saw them in the newspaper because they're a German nanny that would get the German newspaper.
Okay, they were in German newspapers also, apparently. We'll see. I shouldn't say that. One of my, and I can't remember who it was, there's been 3 or 4 people who've been hired in app engineering down in Microchip in the Valley. And a lot of you don't know about the different types of engineering, but app engineering are the people who write app notes. That's one of the things. That's where the name comes from. They also deal with customer problems. So it could be something like you're sitting on a chat room, you know, the really low level people who don't have degrees, sitting on a chat room, looking at the questions, they see the same questions over and over again, they send an answer off for them, looking at the microchip chats. There are people who handle big customers and people who actually buy stuff, and they may have trouble interfacing one of the microchip products into their system, and they will actually have an engineer look at that and help the customer solve their problems. So if you like dealing with people, this is a great engineering job. Not all engineers just sit in front of computers all day. This is one they came up with last year. One customer and one customer only was blowing out the microprocessor every time they hooked it up into their system. So the app engineers had to get together, get one of the failed boards, pull the top off of the IC, look at it under an electron microscope, and they found these guys are actually like blowing holes through here. So they probably had some kind of over voltage problem on this pin. But you have to kind of like dig down, and it's kind of like doing investigations and things like that. So other than most people who get out of college get offered jobs as either test engineers or app engineers. Test engineers are going to be the guys sitting with a big bank of test equipment all day, trying to figure out what's going on and why things are failing, and app engineers deal with customers. If you want jobs other than that, you have to be really good, or you have to get an advanced degree. We're going to watch a movie today. Now that I'm all relaxed, because I suddenly found out that I got a whole week to, no. This is interesting though. I'll go over to YouTube. Don't put my Zoom when things go bad. My sound's turned up. We're gonna play this.
Yeah, we didn't watch this movie like last week.
Oh, I didn't know that. But there, you get the commentary. It's only like 4 minutes long. Okay. So this is an SSD. We all know they're in our computers now, and there's not hard drives. Hard drives are reserved for people who store huge amounts of data. They're working on something that looks like Mentor Graphics. This guy is doing VLSI design. He's actually laying out the chip. Those are the chips. This is what Micron really looks like. I've been there. They have a lot of technicians and engineers doing programming to make sure these machines run correctly. Right now, there's hardly any people in the fab. I didn't see anybody in there. They only let people in because they're dirty when things go really bad. This is the guy with the electron microscope. We met him too. And they're looking at cross sections. They're doing failure analysis on chips to try to figure out how to make them better. And the wire bonding thing is coming in here too. Okay, so we got to test them first. Lots of test engineers. We pick out the ones we like. Don't handle them. And we put it, this is wire bonding. I've done this by hand. It's a pain. Tiny little gold wires go through and connect from the chip into the package. This is plastic. Put a lid on everything to protect it. Silicon oxidizes, it also sees light. That's why the package is black. We get the individual chips and we test them some more. Another bank of test engineers. And then they take them and test them some more. Test them under temperature, environmental, accelerated lifetime testing. We'll talk about that. They have to mark them so they know where they came from. Put them on printed circuit boards and then test them some more. Oh, this is cool. This is wave solder. They put the solder paste down and then the machines come and put the parts down and they run it through a big oven and it solders it for you. You'll mostly be doing repair soldering. There's the finished SSDs. They need to be tested some more. More test engineers. They're starting to put them in the packaging.
Does a person actually package each and every one like that?
They're automating that as much as they can.
That's terrible.
Yeah.
Yeah.
I mean, this was probably made a few years ago, but stamp it, and guess what they do next?
Test it again.
They test it some more, and they put software in it for some reason.
There's a part in this that's coming out that I thought was kind of unrealistic. It was like a person testing a singular SSD. Yeah, right here.
Oh no, this is very real. I will tell you about this in a minute. This is a whole story.
And then she tested it again.
Yes,
Testing it again.
because you don't want it to get to her with it being broken.
Even though something still happens.
Yeah, it does. And then they are usually pretty good about sending it back.
I bought a laptop with blue screening out of the so it's like great.
Okay, so let's stop this. Okay, the thing that you saw, and I got the question I got from the peanut gallery here. I don't know if you heard it or not. There was a part in there where they're taking the SSD and they're putting it in a motherboard, and there's like a whole bunch of motherboards in there. I was in a room that was probably the size of this third floor of the engineering building, and the room is stuffed. There's these what used to be like file cabinets that had a little push button on it that you could roll it to a certain level. And in there are motherboards and PlayStations and all kinds of things, just any piece of electrical equipment you can imagine. There was little hooks from the ceiling that they had computers on. I mean, every conceivable piece of electrical hardware that you can imagine. And the job of this department basically was to take this, and some of it was 5-10 years old, but it may still be out in the field, and people may want to plug a new hard drive into it. So they would have to test it with all kinds of buses and things like that, the different bus standards over the years, different operating systems over the years, and they had a piece of equipment to do it in that room.
I mean, do they test each individual SSD with each of the motherboards?
No, but they kind of like find the right sampling, or if they're having a problem with a particular device, then they can pull it out and plug it in and see what's going on, part of the app engineering process. The other thing, there's another group too that did this. It was great. What was the last PlayStation that came out?
The last PlayStation?
About 2 years ago.
No, it came out like last month.
Wasn't there another one like about, what, 2 years? PlayStation 5 probably.
PlayStation 5 came out a month ago.
Okay, PlayStation 4, whichever one it was. When we were up there 2 years ago, they had PlayStations that were not on the market yet. And there were engineers whose job it was to test the memory in them and to stress test them.
That sounds awesome.
It's a job.
So you make them slow.
Yes. They had,
It's like that's the basic equipment you
but yeah. Okay. So yeah, lots of jobs in engineering.
That would be
Okay.
a fun job. And that's perfect.
Uh-huh.
Yeah, like you said, like that department where it's like
Right.
5 guys in a room. And they just, like, sit
And
there
they just sit there and break things, yeah. But they're playing it. They're coming up with all the different things they can do to try to stress this. Like my son and his best friend one time, they're playing Super Smash Brothers. They found out there was one character they could unlock if they played for 24 hours straight. They would only do this at my house. They took turns sleeping, and they unlocked it.
I miss unlockable characters like that in games.
Okay.
Like, unlock Luigi.
We are recording this.
Unlock Luigi in the first Smash Bros.
This is real engineering.
Oh, that's what it was.
Yeah, even though Luigi was just green.
Oh yeah, I have to do this. We're going to talk about kind of a review. It's kind of I'll keep it at the level of 188 because I realize you're not learning whatchamacallit, you're not learning transmission line theory in 364 because Dr. Kippel's not teaching it anymore. I don't care who's teaching it, but Dr. Kippel's not teaching it anymore. She did it a very practical viewpoint on 364. Remember from EE490, if I have an impedance, Z, and I'm driving this with some power, and I want to drive a load that does something useful, and we want to get the maximum power to the load. The load could be big booming speakers, it could be an antenna, it could be another amplifier, but if we want to get the maximum power to the load, the thing we do is we make ZL equal to the conjugate of whatever Z is. And I'm going to call this Z0, so I won't mess you guys up, because I'll use that probably consistently. So you make it the conjugate of Z0, and that gives you maximum power to the load. People who took 490 in the fall probably have heard this before, but any transmission line, any wire, any pin on an IC has inductance and capacitance to it. And the way we model that transmission line is we make, and we assume it's lossless because you want to have really low resistance in your wires. So your R's are pretty much 0. So for a lossless transmission line, this is the abbreviated version, the way I model it is an infinitesimally small inductance in series with infinitesimally small parasitic capacitances in parallel, and we integrate along the line and we can figure out what's going on. But the big point here is, if I'm an IC, from an IC designer's point of view, I'm an IC designer and I've got a pad on my IC. This is going to go to those little, one of those little wire bondy thingies we just saw in the video. Don't do this by hand. I've done it before. I've done it exactly twice. It took me a week. And this is going to go, so this is the pad on the IC, and then I get a wire bond, and then I get a pin. And the pin is what the printed circuit board designer is going to connect to. And this is going to go to a little trace on a printed circuit board. It looks like a wire, but it's running, it's actually printed, and it's running across the IC. So this is what I'm going to call a PCB trace. And then this is connected, hopefully, to something else. This is connected to another IC. Now, as an integrated circuit integrated circuit engineer, the only things I can control are this region right in here. I have no control over the printed circuit board trace, and I have no control over the ICs that it's being connected to. These right here, this part right here, is effectively my Z load. It has characteristic impedance. These PCB traces have inductance and capacitance associated with it that are going to be part of the Z load. The integrated circuits that it's attached to are going to be part of that Z load, and I have no control over them whatsoever. And this is where we're going to start today. Okay, I have no control over what crazy PCB designer did. Back in 490 in the fall, I had no control over what crazy IC designer did. Yeah, I've worked both sides of that. So we're going to look at some of the output circuitry, and we're going to start going through that path really quickly, not in a lot of detail yet. This is the irritated diagram from one of the pre-lectures a while ago. We're going to start at the pin here today and talk briefly about each one of these things that fall along the path. Some of them are going to end up in project 2, particularly these right drivers, and we'll talk about those and the way they look. And then we'll look at the output path. Okay, that's the goal of today. So the input buffer, same problem. Now, when we're thinking about signals coming in from the printed circuit board, we have no control over how strong those signals are. Are they the right logic levels, or are they just close to the right logic levels? What their impedance is. So the first thing you want to do when you're at the pad and you're looking at something coming, a signal that's coming into the IC. The first thing I want to do, since I have no idea what they've done, is I want to put a big buffer on it that I know will be capable of driving all the currents inside the IC that this needs to drive, that it'll be capable of driving them fast enough, they'll have a low enough output impedance that it'll do that, and that it will have the right voltage levels on the output. When in doubt, when you have no control over what the other guys did, you always buffer. You've heard me say that before. Yes, of course. Okay, deja vu, 490 in the fall. The point of that class is like always buffer. Buffer. So back in the early days of DRAM, our pens coming in were single-ended. That means that there was a single data line out here, D0, and it's not referenced to its own personal ground. It's referenced to board ground, possibly. We were dealing with TTL in the glory days, and the reason why I call it the glory days is because the voltages were high enough. They're 5 volts. The power was high enough, 4 milliamps, and the speed was slow enough, kilohertz, maybe megahertz, that the signals, we didn't have to worry about all the RF effects on the board. Then things started speeding up and voltages got lower. So what we had to do is we had to go to like differential configurations. D0 is now referenced to its own personal ground. So I know that this is the ground from the signal that D0 is relative to, so that the voltages are no longer at 2 volts and 0.8 volts. They may be at 0.1 volt and 0.6 volts. Not a lot of difference in there. So I want to make sure I have a good solid ground reference for that. The signals are getting much faster. Instead of kilohertz and megahertz, now we're talking gigahertz. Serious RF with digital signals. We have to start dealing with these RF effects, these transmission line effects on the board. What they got away with for a while is on the specifications, they would publish what the capacitance was that their PCB friends had, crazy people, had to meet. You never think of the engineers that you're not working with as being safe or as being capable. You always have to be suspicious of them. If you're not, it's going to get you. But what they did is the memory designers would say, okay, this is the capacitance you have to be able to drive. And you'd have to be able to meet that capacitance spec. And that was what the system designers, the PCB designers, would have to look up for that particular chip to make sure that their output buffer could handle the capacitance at this input pin. There is analog engineering, analog considerations, even in the digital world. This is why it was so much easier. I think I said this in 280 yesterday, not to you guys, but it's so much easier to take an analog engineer and train him to be a digital engineer than it is to take a digital engineer and train him to be an analog engineer. But there are analog considerations now that you guys are going to have to worry about. It's much easier to take a custom IC design digital engineer and train them to be an FPGA designer than it is to go the other way. Remembered that. I'm taking 310. Good old 310. I'm learning sloppy electronics. Okay, so this is an input buffer. And let's look at the pieces of this and figure out what it does. I've got the data coming in. This is coming in from the outside world. And I want to not always read the data, but sometimes enable it. This is kind of a version of that tri-state buffer we were looking at in the last class. If my enable is low, this transistor turns on and you can get power to the rest of the chip. So this is like a tri-state right here. We'll draw this one and what this looks like. It's a tri-state buffer and enable is active low, it's got the star, and we have data coming in. That's all that branch of the circuit does. This one right here is fixing that floating node problem from 380 with pass transistors, because if this is not enabled, if enable's not true, I want to turn this transistor on to pull that node to ground. So that's all it's doing, is fixing the floating node problem. And at this point, I want a good standard CMOS buffer. So I'm going to put an inverter in there. This is inverting and this is inverting. So we have two levels of inversion here. The latch is also inverting, that's 3. And this is a 4th version right there. Wait, it's a damn latch, okay. Okay, I take the output from that buffer and I latch it. So I latch it on this signal called trap. I don't know what the purpose of trap was, but it's obviously to latch this in when I want, when the data is valid, trap goes low and latches the data in, sends it to another buffer, and it goes out to the rest of the chip. Because this might have to go, the data may have to go to several locations. So you want to make sure it's good and buffered. It's okay. You haven't gotten to the really bad schematics yet. You're just
really trying to stay away from
okay. Okay. So another thing we have to worry about is on these input pins, when we start going up to higher frequencies. Remember I said that we did this. We want to match my load, and my load in this case is the data pin, to whatever it sees. We won't go that far yet. So printed circuit boards are amazing in that if you're given a certain width of transmission line and a certain technology, you know the characteristic impedance, and printed circuit boards are consistent enough that there's really just a range of impedances, characteristic impedances you can get from that. So this is kind of known within a range. So one thing I can do is I can use RF techniques that you haven't been taught yet, unless you can learn those down at ASU. You can learn those on the job in the Valley. I didn't know anything when I started. I didn't know anything really when I started working. But you can match the impedance, and this is an impedance matching network here, of what the data lines see internally on your chip to what the kind of somewhere in the middle of the expected ranges of the Z naughts you're going to get from a printed circuit board. That will give you a Z naught that's closer to ZL through this matching network. And you can have a better match. We'll get into some, we'll get into this in a lot more detail later on, like right before the midterm exam. And this is kind of a sloppy way of doing it, so I don't want to talk about it too much. Okay, We want to look at a differential amplifier. You've heard that word before, haven't you? 380. Remember, it was the evil circuit? I took a whole class on differential amplifiers and integrated circuits for some reason or another. But this is what this is. And if you look at this circuit, this is just what you saw in 380. I've got my differential pair right here, the NMOS transistors. This bias is acting as a current source. That's why I tell people 380 is prerequisite. Right here, the PMOS transistors up on the top are an active load. They're acting like the resistor on the old board designs, but they're much more reliable because it's easier to match the transistors, and they basically just drop voltage. So you can have the correct voltages here. Now X, if this signal is trying to drive high, it's going through a PMOS transistor. PMOS transistors can drive all the way up to VCC. Remember that lose a threshold thing from EE490. And coming through the other side to get to ground, it has to pass through a NMOS transistor that has trouble driving all the way down to ground, and a second transistor that's going to have, that can drive all the way to ground, as long as your current source doesn't work, as long as your current source is still working. But to keep the current source working, you've got to have some voltage drop across it. There's a minimum VDS to keep this thing working. So I can only drive it down as far as VCC minus VDS bias. I'm losing some noise margin there. I can clean that up somewhat by running it through a buffer, AKA an inverter. What is this doing? If we look at this, remember a differential, this is as much as you need to know for this class. We're not going to go through and do the common mode rejection ratio or anything like that. What is this thing right here? It's a differential amp. So if I want to get it in my head how this thing's working, I draw it as an op amp. Yeah, I know. That's because I'm in the engineering building. Which one do I know yet? No, I don't. Doesn't matter. Okay, one of these is the plus terminal, one of them is the minus terminal. We won't worry about too much about it. But I've got two signals going into it. There's no feedback loop connecting the inputs into the output. So this looks like an open loop op amp out, and V out in this case is X. And my inputs are Vref and N. I should be, okay. Our Vref and N. It's open loop, so this is a comparator. Anytime you have an open loop op amp, it's going to act like a comparator. In I've got those swapped. We'll make this minus and this plus. Okay. So as long as the input is less than Vref, what I'm going to get out of here is, and it's powered with VDD and ground. My output, if the input is less than Vref, my V out X equals 0. Will be grounded. If the input goes higher than Vref, then X equals VDD. So it's a simple comparator. I can set a voltage reference for the device and say, okay, If my data input signal is greater than 0.6 volts, I'm going to call it a 1. It's less than 6.6 volts, I can call it a 0. I can kind of clean up some of the garbage that the PCB designer throws at me. And then I buffer it. Never leave the buffer out. Always buffer. Okay, so yeah, we talked about that. This is called an N flavor. The kind of the language is it's an N flavor differential amplifier, and we call it N flavor because the transistors that form the differential pair are NMOS. I could do a P flavor of this and make those PMOS and then make those NMOS, and then I'd have, we'll look at that circuit later, and then I would have to change this transistor too. What? NMOS flavored ice cream. Oh God. Silicon and arsenic and
Oh boy.
I don't want NMOS in my ice cream. Okay. Now, duty cycle distortion. What's going to happen here is when I pull it up, I'm going through a P. When I try to pull Z up, I'm pulling it up through a PMOS. And when I'm trying to pull it down, I'm pulling it down through two NMOSs. They're not going to have the same delay. So if this is something like a clock signal, what would happen to my clock signal is it would go up faster and maybe go down slower, which makes it appear like it's not really running at 50%. We want to keep those impedances as matched as we possibly can. When you start working, you'll find out if you care about this or not. And if you do, then you'll learn a lot about it. And then you buffer it with an inverter. I always buffer it. Okay. Self-biasing, in this case, we have the current transistor is right here. It's next to the op amp, and it's being biased. The reference voltage is coming off of this circuit, so we call this being self-biased. I'm not running a current source all over the chip to this one particular device to do its current, and I'm not running a reference voltage to this gate here to set the current. It is pretty much being driven, the current through here is being driven by the gates of those transistors. Well, they all have to go off somewhere. Oh, that comes from the input. Okay. If I want to get this to go rail to rail, I can add a second diff amp in here. The N1, be consistent and nothing else. Okay. I know I can't. Okay. Right. That's not right. That's not right. Okay. The N flavor, well, I do not want to go there yet. This one, can drive it all the way to VCC. This one can drive it all the way to ground. So if I put two of them in there, I'm comparing X, my input, to some reference value Y, and Z is my output. It can go from 0 to VDD. So I've cleaned up the signal. I've added some more stuff. I made my output pin pad bigger. Generally, if you look at designs of integrated circuits, the things that are sitting right next to the output pad, the circuitry for that is much bigger than anything else inside the IC. we don't get down to the 5 nanometer level in one step. You have to have this the buffer on the output pad in order to do that. This is the schematic symbol. It's just a buffer. It's an open loop op amp. It's acting as a comparator. Which one's which? This is, why is that? This is the negative input. This is the positive input. Let me see if I can explain that little footnote down there. This is the positive. As X goes up, it's pulling down the output and the output decreases. Going the other way, as Y goes up, the output increases. And the difference, yeah, okay, it's linear in between there, but we're thinking about this digitally, so let's not go there. Okay, so we've got my pen. It's got to go to some data input buffer. There's also got to be ESD protection on the pen because you don't know how crazy the people handling it are. And the next thing we want to talk about is the muxes. So I've only got one pin for D0, but D0 has to go to the correct part of the memory array, the correct bank. It has to go to the correct subarray in that bank, and it has to go, where else does it have to go? It has to go to the right column in the bank. So we've got to have something in here to decide exactly where we're going to send it. And these schematics drive me crazy. Okay, they're not drawn really well, and Dr. Brower's interpretations of this are not exactly
Correct.
Yeah, they're not, okay. So here's an example. And I worked through, I looked at this. I had time to actually look at my slides today. I'm really proud of myself. So I've got a word size that's 1. I only want to have 1 bit at a time coming out. What I can do, I've got 4 data inputs. So what I'm going to do is I'm going to type D0 in here. I choose, and then maybe D1 here. D2, D3. Well, this is giving me 4 bits at a time. So I don't use these. I tie my data bit coming in here, and I select the X1 option, and I send it out to the subarray. I could also put it through one of the other 3, depending upon where it needed to go. But I only need 1 data path in here because I've only got 1 bit at a time going in, 1 bit at a time going out. Now we're going to look at the X2 option. So for X2, I'm going to be addressing 2 bits or reading 2 bits at the same time. So in that case, this is going to D0, this is going to D1. Rest of them aren't used. I've only got 2 bits. And D0 will go to wherever it needs to go, and D1 will go to wherever it needs to go. If I want to have 4 bits coming in, scribbling. 4 bits, I'm going to have to route the bits to the X4 option and select that. So D0, D1, D2, D3, all 4 bits come in here off of their pads. I choose the X4 option and it goes to the 4 different places I'm reading from. So that's what these multiplexers do. And there's probably a whole 10 guys figuring out these multiplexers. and getting it right and changing it for the next chip, etc. Okay. When you are the printed circuit board designer and you're given a choice between, oh, I'm going to buy this chip and it can have a 4-bit word coming out, an 8-bit word coming out, or a 16-bit word coming out, you cannot change that on the fly. And that's the point of this slide, because when I make my printed circuit board and I solder this thing down, this has different values. This has different meanings upon which one I chose. So this is, once you decide for your system, you're stuck with your decision. Another thing to point, pins change based upon what you want the outputs to be. Another thing to see here is, let's look at the number of VDD pins. Oh, great. There's VDDQ, there's VSSQ, that's like ground, VDDQ, VSSQ, VDD, VDD, there's another VDD up the top I can't touch. There's a VSS here I can't touch. VSSQ, VDDQ, VSSQ. Look at the number of ground and power pins that are on this chip. There's another one.
What is NC?
No connect.
Oh, just they float.
Yes.
The dashes are don't care.
The dashes are probably, nope, I don't. You're gonna need a write enable. So I think those are the same for all three. Yeah, okay. We've got this one chip we just got from Everspin down in Phoenix. And they normally, for memory, most people would want to read out a 0 or a 1, right? Okay. But no, I work in Dr. Campo's lab. Okay, so we want to read out the analog value of the 0 or the 1, the actual analog voltage. That's not available because it goes through buffers to make sure it's the same 0 and 1 every single time. They have pins on this package that are labeled NC, no connect, and even more harsh, DNC, do not connect. And those are the pins that we have to use to get the analog voltages out. A lot of times these IC companies, they want to be able to look at internal voltages in the chip, but they don't want anyone doing it. So they create these things called test modes, and you can write to registers and give it like, put it in a certain state with the test mode that allows you to look at things like the analog voltage at the pin. So that's basically how we're using it. And we're connecting the DNC pin, and we're connecting the no connect pins. And we're writing a weird cryptic thing into it to make it come out analog. Yeah. It can be done. Everybody does stuff like this, because once you've built the IC, you can't probe it. So you put these test modes in there so you can probe critical voltages inside there. Yes. They usually call that, some departments called design for testability. Okay. Real world. Okay, so here's an sort of actual data write mux. I don't know who to yell at, Keith or Brower. I've got different options here. Obviously, to me, this thing has to be duplicated twice. Partially because I want 16 output pins here, and this one only has 8. That was my first red flag here. So I'd really want this to be twice as big as what's shown. So there would be another bank of this someplace else. We'll call this lower byte. This is how I figured out that was that little symbol in the last class or so was a 1-to-1 mux, because it's labeled here.
Yeah.
Okay. This is a 1-to-1 mux that's always enabled. It's a buffer. Okay. I've got 2 of these that are always enabled. And whether I have 4 outputs, 8 outputs, or 16 outputs, 2 and the additional 2 from my other imaginary mux out here will give me 4 outputs total. Okay, so these are always enabled. If I choose, let's go down here. I'll probably grouse about this later on because there's something I didn't like about this. If I want to enable the 16-bit mode, I'd have to enable all 8 of these multiplexers. So that 16-bit line has to enable all of them. And you can see that the 16-bit is connected here, 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 and here. So when the 16-bit's true, I can enable all the multiplexers. I knew there'd be a problem here somewhere. I found it. I'll just not talk about it. When I go to the 8-bit thingy here, I need to enable half of these multiplexers. So the 8 is the middle line, and it's able to enable this one, and the ones that are always enabled. It enables 4 of them. You want to see the thing I don't like about the schematic?
Sure.
Yeah, that's just going to the wrong line. Okay.
Wait, what?
There's a mistake on the schematic, and Dr. Brower's not the only one who finds these things. So 16 goes to, no, 16's not going to all of them. These are going, some of these are going to 4. This should go to 16. That should go to 16. It's going to the 4 line. Okay. Just get over it. It's a cartoon of a schematic. This is important. Now let's think about this. This shows up on project 2, these write drivers. And they're drawn here as tri-state buffers. And that's all you have to do is you go to generic 13 where you found your NMOS, and you go generic 13 like logic tri-state buffer. That one will be simulatable. So there's already tri-state buffer built for you. What's going on here? When I'm writing to the chip, data's coming out this way, and we want it to go through a buffer. When I'm reading from the chip, the data's coming out of the chip and writing to these same I/O lines as the data that we're reading and the data that we're writing share the same lines. So in order to do that, when I'm reading from the array, I have to turn these things off. So what you want to do is to add to project 2, and you can get these in the generic 13 library, is you can get a tri-state buffer, and it doesn't matter if it's inverting or not, because I'll overlook that. This is some kind of write enable, is what I called it. And this is coming from the data pen. And this is going to my, what do we call them? We call them DL in the project. And this is going to DL0, DL1. So my data pen comes in here, goes through there. We got to give it a different name on the other side of the buffer. If you name them the same thing, Mentor Graphics does this wonderful thing. It's called Connect by Naming Convention. Things that are named the same are automatically connected together, and it won't work. Don't do that. So call this something else than what you call these. And that will be part of project 2. Project 2 is going to take a little bit more time than project 1. You've got about 3 or 4 weeks to work on it. I recommend starting early. Yeah.
Starting now.
Yeah, that wouldn't hurt. We already know a lot of the things you need for project 2. You're just going to have to basically do a simulation. Okay. So for the right driver, I don't even want to talk about that one. Where's the tri-state in here? I don't know where the tri-state. Okay, so this right here kind of gives you a good idea of what you're going to need for your project. You're going to build a, later on you build a sense amp. We don't put a sense amp in project 2. We just have these right drivers going directly to your 2x2 array. And the 2x2 array is going to write to these lines and be disabled otherwise. Later on, we're going to put the sense amp in there. So this the IO transistors, when the column is selected for that particular column, we only have 2 of them, then those IO transistors are going to enable the sense amp to be connected to the 2x2 array. So it's yet a third thing we're going to put on the bus. That irritates me, sorry. It's still like, no, Chris. Sorry. It's like last semester I had people texting me in class. It was usually the TAs, and so I just don't, still, I can't think. Okay. The timing for project 2 is, well, the first thing I have to do is I'm going to pre-charge the bus to VCC over 2. Then I turn word line on, and part of the project is to turn in a hand-drawn timing diagram. No, it's not going to look like this, but the timing's going to be the same. So I need to pre-charge. The way you pre-charge is you make equilibriate true. Then I turn the word line on. And as I turn the word line on, you'll actually see this going up or down based upon whether you've written a 0 or a 1 into that capacitor. Later on, we'll worry about the sense amp. Draw the timing diagram first so you don't go batty programming your pulse sources. We're going to look at the read path really quickly. I've got 15 minutes. I have 72. Oh, I'm not finishing this today. Don't want to talk about that. Don't want to talk about that. Okay. So this IO bias circuit is actually the sizes of these transistors, and the timing on these things right here is such that I can control the very fine tune these volt IO lines. In the idle state, when the RAS active low is high, no, this row is not addressed. I just want to leave the IO lines biased to VCC. That keeps them from picking up noise. Right before the column select goes true, I'm going to change the bias on them to VCC minus a threshold. And then after chip select, they're going to go up and down very slightly. I think this, no, never mind. I think this should be VCC 2. I'm just going to change that. And then during the write cycle, they get driven to the rail. So these things have to, the IO lines have to be set up at the right voltages at the right time. This is where the analog engineers get involved. Before RAS comes down, the IO lines are at VCC. Right after RAS, during the read cycle, we want them up here. And then as we start to turn on the sense amp, they're going to start to be driven to the rail. This is like, is there, no, it's not. This is like a couple of nanoseconds in here. It's less than a clock cycle. So that circuit has got to be able to do that also. They're wrong.
They're just,
Let's talk about something that this circuit, I don't know how to, it's like art history. I just don't know what to say that will make it meaningful to you. This one I can make meaningful to you. It's a more simpler version of the right driver. What we have here is we have an enable for right. This is my right enable right here. Right enable. So if it is high, these gates are going to be in the same state no matter what. DW is another name for my data line. I've got to give it multiple names to keep Metagraphics from, or my whatever my EDA tool is, from auto connecting them, is coming in here. So this is just basically data. It's a differential. So this is, I'll just do it this way. This is data not, active low coming in here. So if right is low, is that true? I'm really not liking this. Oh yeah, okay, I got it. If right is high, let's just look at the case when it's not enabled. When right is high, the OR is high no matter what. So this is low no matter what. If this is low, then the not of that is high. So my IO line, and then this, if this is high, this turns off. Did I really want to start this? Okay, if right is high, this is, I should write it down. If this one is 1, then it doesn't matter, I get a 0 here. This is 1, I'm going to get a 0 here. So this transistor is off. This transistor is off. The not of that is high. So this one is off. And this is 0, this is off. All the transistors on the output stage are off if my right equals 1. Now, if right equals 0, what happens? If this goes low, now the data matters. So depending upon what the state of the data is, if this is, oh yeah, I can't forget that. If this is 0, if the data is 0 here, then 0 or 0 is 0, which is 1. This one's 1. Not data would have to be high. So 0, 1 is 1, which makes this 0 still. So 0 turns on that transistor and drives my data high. Wait, if data is 0, if this is 0, I get a 1 here. Yeah, if this is 0, I get a 1 here. This one goes on. I'm suspicious of this. This is a 1. This one goes on. If this is 1 and 1, is 1 or 1 is 1, and that's 0. So 0 goes here. I invert it, it becomes a 1. This transistor is off. Yes. So my data line actually goes low. So this is inverting. No, my data is 0. It's not inverting. I have a 1 here. 1 or, oh, great. That line's 0. This is off. This line is 1, it gets inverted, it's a 0, so this one comes on. My IO star is now high. So I put a 0 in, I get a 0 out, and I get a 1 out there. You can size these transistors. These are your driver transistors. You size them to be as big as you need to be to drive the current that the IO line has to drive, because it's a big long line. It goes all over the chip, and will handle the current capacity that you need to drive and the capacitance that you need to drive. You have control over that now. That's the basic rate driver. Am I done? Yes, I'm done. Yeah. I'm officially a day behind, but we've got spring break to catch up. Or not a spring break.
Not a spring break.
And I've decided I'm just going to call it pseudo spring break, since on my schedule you have nothing due that week.
Yeah.
And no exams. I'm going to leave it like that.
We have the exam right before spring break.
The exam's right before pseudo spring break. Yeah, but nobody would be going anywhere. I had big plans for spring break. By that time, my second vaccine, it'll be a couple weeks after my second vaccination, I'll be free to do wild and crazy things like eat in public. Scandalous. What else do we have? Any questions? We got about 5 minutes.
I got it.
Yeah.
I'm just confused on what you're asking for number 4.
On homework 2?
For the column views block in the figure,
Oh,
draw the correct TAM star decoding circuit.
that one. This is homework 2. Homework 2. Okay, so this is homework 2, number 4. Draw the correct CAM decoding circuit. So what you do is you go to the book. What I did is I printed out a copy of the diagram in the book, and I don't have it with me, for the CAM decoding circuit.
I'm assuming it's probably in like the chapters we got recently.
Yes, and I'll let you look at it. It looks like this.
Figure 4.6.
Okay, figure 4.6. So you draw that, or you do what I did. I didn't want to have to draw this again.
Okay, so
And the thing you want to do here is you want to have it so it decodes that particular circuit decodes the correct value. Decoding circuit. We wanted to. Great. Yeah. F0, F1, F1 star, F1 star. Let me think about this. Oh. So the first one has to connect, the first level has an output of CA01 of 0. So it's got to decode, the one furthest to the left is decoding state 0.
Mhm.
If it's decoding state 0, we want this to be true if F0 star, F0 star. We want it to be true when F0 is low and F1 is low. So that one's okay, because you're decoding a 0, 0 from that one. If we want to decode a 0, 1 in the second column from the left, it's easier if we just look at the same diagram. Maybe we should just talk about this while we're looking at the diagram. Then what we want here is we want a 1 out So 1 would be F0. Oh, that is right. Is going to F0 star. So the least significant bit is 1. And the more significant bit is 0. So you're just going to have to flip those. And I'm just going to have to show you the picture, and I don't think anybody else cares. So the rest of you guys can go, and I'm going to go explain this to Zach.
Okay, so it's way easier to see this picture. Okay, so for zeros, if you get a 0, 0 here, this is going to be 0, 1. So 0, 0, I want F0 on this one and F1 on this one. And I want F0s, both of these to be 0. What I did is I just started labeling. So this one is 0, 1. Sorry, is it 1? Oh, yeah, I just wrote it backwards. Okay, so this is 1, 0. So then I'm going to flip the polarity on F0 and flip the polarity on F0 on one original. And that would give me 0. This is 3, not more. So this is 3, so this should be, they should both be low, so it should be flipped from this one. So they're both stars here and they're both not stars here. There's probably a wire. Yeah. I decided I wanted both. So this one has the most significant bit. It's the original one, so that F1 and F0. And how they're connected doesn't matter if you connect them by means connection. I think there is an error in that somewhere of how the wires are going. Now, camp can only go high if one of those states is here.
So like F0 and F1, select these states,
Right,
and then the output is determined on whatever state you select.
right. They basically become those states. And if one of those states is true, you can go straight. Column address. I'm going to see how it goes, right? There may be a few people, well, I mean, here be a few people on Zoom.
Okay, yeah.
So there's a problem with the wiring, or these aren't wired up, and I just changed it instead of using wiring. I changed it to connecting by naming convention, because it was driving me batty.
Yeah, because I'm gonna try to knock out try to leave the homework tonight, I think, so that
Okay.
if I have any questions, I can bring them to you tomorrow.
Yeah,
I don't think it was too bad.
Yeah, 3B is just draw, what is that? Draw an AND gate. Draw 4 AND gates using transistors.
Oh, that's easy.
Yeah.
I
Well,
learned 2 and wrote, etc. Should I write the other 2?
Sean's grading it. Yeah,
We'll find donuts then.
okay.
No, they don't have the chocolate donuts at Sam's Club anymore. And which is what Sean's been asking for.
Okay. Well, what you could do is maybe go to Dunkin' Donuts and buy him a chocolate donut and say, Sean, help me with my homework.
Oh yeah, I'm grabbing lunch with Sean tomorrow, actually. When he gets out of class.
Okay.
Maybe I'll ask him if